No problem. So let's get started. Welcome back to the second half of the sessions today. So we have Todd Gamblin from Lawrence Livermore National Lab. Will be presenting this session. He's a senior principal MTS in Livermore Computing Advanced Technology Office. He created Spack, as many of you know, a popular open source HPC package management tool, which is growing very lot of popularity. He leads the packaging technologies project in the US Exascale computing projects and Livermore's DevRamp project on developers productive and an LNNL strategic initiative on software integration and dependency management. His research interests include dependency management, software engineering, parallel computing, performance measurement, and performance analysis. So he has an electrical engineering degree with first class honors from Queen's University, Canada, and he's also a registered professional engineer. So we have been working.
That's actually wrong.
Pardon me?
I went to UNC, but yeah.
Oh, there was something wrong here. Oh,
no worries. Yeah.
There was a cut and paste error. My apology, I think. So MVAPICH team has been working with Todd and his team on the Spack integration. So today we'll be talking about some of the updates on binary cache handling in Spack. So Todd, please carry on.
Oh, okay. Here, let me share my screen. Can people see my screen?
It is just coming up. Yes. Okay. The presentation mode, you may need to.
Is it presenting right now?
Yeah. Good.
Is it good, or is it showing the presenter screen?
No, it is correct now.
All right, cool.
It's correct. Yeah.
Okay. So I was super happy maybe a year ago or maybe a little more when the MVAPICH folks started using binary packages for their Spack distribution. But I guess I would say that they may have jumped the gun on this and done it before we were really ready to start distributing binaries in a smooth way in Spack. So I would say that the usage of binary caches by the MVAPICH 2 folks has really helped us understand what the pain points are for binary packaging. And I guess I'll get to that, but I want to talk about just Spack in general a little bit first. So for people who don't know Spack, it's a package manager, like DK said. We have actually over 4,000 monthly users on the doc site now, and it's used all over the world. It's been super beneficial for us at Livermore because we get so many contributions from the external community. So essentially, package contributions, most of them actually come from outside Livermore. It was originally a Livermore project up through maybe 2015, and then we really started getting outside contributions, and the numbers have just grown. So we're trying to make Spack to be sort of a de facto package manager for HPC. Originally, Spack was just a source package manager, and so it builds everything from source for you. And lately, people have really started getting interested in the build cache functionality in it for both things like the proprietary binaries that the MVAPICH folks are distributing, and just for speeding up workflows. So under ECP, over the past year, people have started doing CI workflows with Spack, and the ability to have a build cache there has been really big because it's brought workflows down from a couple hours to build a huge software stack to minutes because they can install from a cache. So I would say it works pretty well in that usage scenario where you're building locally and you're sort of reusing your own binaries. And what we'd really like to enable is what the MVAPICH folks want, which is being able to distribute binaries broadly to lots of people. And so I'm going to talk about the capabilities that we need for that and what we're doing to address it. Slides are not doing it. I guess I'll just say we're adding a new concretizer into Spack, and the concretizer is sort of the central thing that solves packages. We asked people in a survey this past year what the most important features were for Spack, and I mean, the things that they wanted that are at the top are the ability to reuse existing installs and to reuse packages from binary mirrors. So this is really one of our top most wanted features, is the ability to do this where you know that you have a build available and you really want Spack to use it. E4S, which is ECP's software distribution, has a binary cache with over 37,000 Spack binary packages. And like I said, they've been developing these sort of CI workflows for people using their repository. It's built for lots of different OSs and architectures. The binaries are still generic though, and they're not, the things that are distributed by E4S are not yet optimized for the architecture. And we'd really like to have that in as an optimization criterion. But we're starting to have public binary mirrors. And like I said, they've been able to use this to improve the performance of Cloud CI for certain projects by 10 to 100x, which is good. We are trying to test builds more often and to actually generate a binary mirror like E4S's, but for all of Spack. And actually, if you think what we've added to CI recently is testing in GitLab, where we test about 400 packages and build them on basically every pull request. So if a pull request comes into Spack, we have this environment that describes that E4S distribution from ECP. It goes and kicks off pipelines in AWS. We're adding pipelines at Livermore and at the University of Oregon for that. We actually have a Power 9 pipeline running here. We have x86 64 and soon ARM running in AWS. And essentially, we're building binaries all the time, and we want to make that available as our own public binary mirror. And the other advantage of this is that it ensures that the package builds continue to work. So we've had to build a lot of infrastructure to enable this. To the point where we can actually test every pull request. It's taken a lot of scalability improvements to the cloud infrastructure we're setting up, and a lot of this is actually due to AWS giving us credits to do this. We basically we have a Kubernetes cluster in the cloud that is running all these builds, and we're doing about 12,000 builds a week now, which is quite a few. Basically, we're enabling everyone who submits a pull request to Spack to get their stuff tested in the cloud in this environment. And our hope is that once we get that ironed out, we'll be able to offer public binaries, sort of like the MVAPICH ones all the time. I looked at the MVAPICH website and took a look at the instructions for building MVAPICH 2 GDR from build caches. And I mean, they are rather complicated. And so this is what I mean when I say that I think the MVAPICH workflow, these guys are pioneering distributing things with Spack build caches. And I think just reading through this page helped me understand what the pain points were. So you have to clone Spack, you have to register a bunch of external packages in your config here. So you have to sort of paste some YAML into a config file. You have to get the key for the build cache. We've actually automated this step, so you can run a command instead of having to wget the key and trust it yourself. And the binaries are signed, that's why you have to trust the key. And then you have to install build caches by hash per dependency. So there's this whole loop that you have to go through where you say, I want to install this particular package, and so on. And you have to sort of deal with errors as you encounter them. And I think this whole thing could be much more automated. Eventually you get the right MVAPICH 2 GDR package, and that's cool because you get the optimized MVAPICH 2 GDR package installed on your system. You can use it with your Spack builds. But it would be nice if you could just register the build cache and say, here's the URL for MVAPICH's package repository, and then install stuff and have it use MVAPICH 2 GDR by default. That would be ideal. We don't currently do that. So I'm going to talk a little bit about some of the things that we're adding to make that easier. So one of the steps was register externals, where you have to paste this YAML yourself. What we've done in Spack 0.15 and 0.16 is we've actually added this Spack external find command that you can run, and packages can sort of detect themselves on your system. So instead of you having to write the configuration yourself, CMake and other packages can actually be made configurable by adding a method to them. And when you run Spack external find, this runs, it goes out and finds instances of that package on your system and writes the config itself. This was sort of targeted as a developer feature, but given that MVAPICH 2 actually has dependencies on some pretty deep system dependencies that you wouldn't be able to install with Spack, I think this could help with the installation process. You could basically add the dependencies to Spack, make them detectable. They don't have to be buildable. And then you can find them with this, and it'll add it to the YAML yourself. And I think that could simplify the instructions. The other thing that I think will help here is that we have a new solver in Spack. And just for some background, what Spack does when you say to install a package is it takes the description that the user gives, where you've said, install my program. Say you want to install WarpX. And it tries to figure out what MPI should that thing build with, what versions of all the packages should I use, what variant values and so on should be applied to that package. And it comes up with what we call a concrete spec. and that's called concretization. The original version of Spack and all the ones up to 0.16 had sort of this concretizer that was greedy. And the problem of solving for these versions, doing version solves in a package manager is actually NP hard. And you need a proper solver to do it. So we've started using Klingo, which is an answer set programming solver. And it looks an awful lot like Prolog, and it leverages SAT behind the scenes plus optimization. So essentially now, instead of doing this sort of tree algorithm that we used to have, where we would pick versions and sometimes pick the wrong one, pick one that would conflict with something else later, and we wouldn't be able to backtrack. Now we basically tell the solver everything about all the packages that could be dependencies of what you asked for, all the things we know about the externals and things on the system, and it goes and solves that. It generates something like 30 or 40,000 facts that go into this solve. And there's this small logic program that's 700 or 800 lines that then takes that and turns it into a concrete spec for us with a full backtracking, optimizing SAT algorithm. And it's been easier for us to maintain. The code, look, it's very declarative. It's pretty simple for us to write, and we can do pretty complicated things in it. The backtracking has enabled us to resolve much bigger and more complex package configurations. Currently, it requires the user to install Klingo, or initially it required the user to install Klingo themselves. And what we've been fighting with over the past year is we really want to leverage all these capabilities, but we haven't made this default yet because it requires you to install the solver. So essentially, Spack now has its own dependency on this package. It has been a big deal for package authors as well. Before, you may have had to write sort of complex cross products of constraints, like if you depend on foo plus a plus b, when plus a plus b, and you want to sort of propagate these variants to your dependencies, you had to write this big complicated thing. Now the new concretizer lets you sort of orthogonalize those and not bear the combinatorial burden in your package. So you can just write sort of simpler dependency constraints. And you can do things like specializing, which this did not work before in the greedy concretizer. But if you say depend on BLAS, or if you depend on, I don't know, MPI, and when you depend on a particular MPI, you need some specific options. Now you can specialize that. So basically, this says depends on BLAS. This says if I pick OpenBLAS as my BLAS implementation, then I'm going to specifically say that for that BLAS implementation, I want the thread model to be OpenMP. And this gets integrated into the solve, and it'll find a satisfying solution. Whereas before, this would just result in a conflict, because basically it would make a choice for the BLAS implementation, or for OpenBLAS, ignore this, and then come to this constraint and say, oh, it's a conflict. So backtracking has helped a lot. This has fixed a lot of bugs in Spack. So if you search on the repo, there are tons of issues that have been fixed by the new concretizer, where now we're doing something more sensible, and so people seem to like it. They want to use it, but again, it's a C++ library. We have to we have to build this whole thing to get the solver working, and so it's a chicken and egg problem. Concretization is sort of the first thing you have to do to install anything. We would have to do it to construct this graph. And the dependencies for Klingo are actually pretty complicated. If you want to build with the Python support that we need, getting all the right Python libraries in place is a challenge. And it requires C++ 14, which is another problem. You don't know that the user has a C++ 14 compiler, so we don't actually know that we can bootstrap this from source. So what we've done is, for step 1 in 0.16, we just made the new concretizer available, and you could set it to say, use Klingo as the concretizer. You could install that yourself using Spack, basically bootstrap it using the old concretizer, and then run Spack with the new with the Python that you built. It's not ideal because you have to build a lot of stuff to get going. Step 2, this is in 0.16.2. We added this fairly recently. We will bootstrap automatically from source. So if you do have a C++ 14 compiler, Spack will build you Klingo automatically. It'll load it into Spack's own Python instance, and then it can get it going. And then finally, what we have just gotten working is that we're actually bootstrapping from binaries. And this simplifies things a lot. It eliminates all the build dependencies that we would have to install to get Klingo bootstrap from source. So that's nice. It the amount of stuff that we have to install now is a few megabytes versus, you know, all of the archives and all the builds. And so, and it's fast. So we don't have to build from source anymore, although users can still opt out and build from source if they want to or if they have to. But we have a public binary repo with builds that are done in GitHub Actions. So you can actually go, you can see the builds that we do to bootstrap the new concretizer. And you know, so if you have doubts about their, you know, authenticity or the provenance of them, you can actually see where we build them. They're completely transparent. And Spack will install them. They're built very portably. So we actually build in a CentOS 5 image to use a really old glibc. And we have these bootstrapped on Mac OS Linux and different architectures. So essentially now, if you say Spack install something, it goes and grabs these binaries first, and then you're set. They're installed for the rest of the time that you're using Spack, and we don't have to deal with this complicated source bootstrapping process anymore. So now that we have that, we have a number of improvements that we've made to Spack to sort of improve the experience with build caching. The first one is that, you know, if hash caching is something that we haven't done in the past, hashes in Spack are created by this concretization process, but Spack doesn't actually remember them unless they get installed. So we have a database of installed packages. If you refer to one by these hashes, which identify a unique configuration, we don't necessarily, we don't remember that unless you actually install the package. And that can be kind of unsatisfying. If you say spec-l HDF5 and you get this configuration of HDF5, and then you decide that you only want to install lib event the way that HDF5 would build it, if you refer to that and say spec that thing, it's here, we talked about it, we know what it is here, but Spack's forgotten about it by the time that you actually refer to it. So we're adding a cache to Spack so that basically if we show you a configuration of anything that has a hash, we'll actually remember the hash and remember what it means later. So this is useful for build caches because essentially when you register the MVAPICH GDR build cache and you say what's in it, you get a list of hashes. And if you try to install those, it says, oh, you can't install that. That's specific hashes. I don't know what that means. And you know, the way that Spack has previously dealt with build caches is we sort of expected you to have the same configuration as the guy who built the binary. And so the reuse was opportunistic. Basically, if you concretize to the same thing and you get the same hashes as what's in the build cache, we would go and say, oh, we already have that hash, and we'd pull it down for you and install it. But you know, if you wanted to do something specific that Spack couldn't concretize, or if you had slightly different configuration to what the guy who built the package was using, we would miss and we wouldn't install the right thing. So this will let you refer to something specific. But the other thing that we're adding is hash reuse. And so with this new concretizer, we have this ability to add optimization criteria. And we can tell it to essentially maximize the number of hashes that are included in a build. Or probably better, minimize the number of builds versus binary installs. So essentially, if you have hashes available, use them. Use those binary packages from the mirror instead of trying to build the package yourself. We need to tell the concretizer about the hashes in advance, but this is actually pretty simple using AFP. So we have a prototype implementation of a reusing concretizer that looks kind of like this. Essentially, we would see a build cache, and you register it with a URL. We tell Spack about all the installed packages, and this basically is if OpenSSL is in the build cache, it has a particular hash. If you use that hash, it implies all of these constraints over everything else in the solve. So essentially, what we're saying is, you can do this, but the rest of your graph has to not conflict with any of these things. Otherwise, we won't be able to resolve with that particular thing. So it's not just reusing, right? It's making sure that the thing that you reuse is compatible with what you're going to build. And so we have to know about all these constraints. It turns out that telling the concretizer to reuse hashes is not that hard. We can say this rule here just says, like, if some package needs to be a node in the graph, the concretizer has the option of choosing one hash for that package. So if it can, it'll find the hash in the build cache, it'll substitute that for the package and use that. If you use that hash, you basically impose all these constraints on everything else in the solve. And essentially, if you chose a hash for a package, it's not built. But if you didn't choose a hash for the package, and if it's not external, then we call it a built package. And basically this last line says, minimize the number of builds that you're doing. And so the result of this looks something like this. Before, if you tried to say, install LLVM from a build cache, and it knew about a bunch of dependencies of LLVM that happened to be in there, it would still say, oh, well, I'm only considering what's in the packages. I'm going to pick the latest versions of everything. I'm going to pick the defaults for the configuration, and I'll end up with these hashes. And so only one of these is actually reused from the build cache, like one version of zlib. With the new concretizer, if you have dependencies of LLVM that you want in the build cache, it's going to try to reuse as many of them as it can to minimize the number of builds that it has to do. And so what you can see here is that this results in way fewer builds and many, many more things installed from binaries than what we had before. So with this stuff, what I think we will be able to do is make it so that users can say, okay, register the MVAPICH GDR build cache and prefer that version of MPI. And then that's all you have to set up. And if you say install MPI programs with Spack, it will reuse the MVAPICH GDR and other binaries from the build cache instead by default. It'll figure out a way to use them if it's possible, and users will be able to install MVAPICH much more easily than they can now. And so hopefully with this stuff, you won't have to have 3 pages of instructions for how to use Spack with MVAPICH. It'll be much simpler. So that's it. Any questions?
Yeah, Todd, first off, thank you. This is awesome. As one of the people who's been maintaining our Spack package and trying to write those instructions, this does look like it's going to make our lives a lot easier. So this should also, like, with the fact that it's going to prefer the packages that are in our build cache, that should eliminate the issue where, like, let's say NVIDIA pushed a new version of CUDA or changed something in that, we're seeing all of our build caches get invalidated.
Yeah, so that may be another thing that we would need to think about. One of the things about Spack's deployment model right now is that we deploy as if built from source. And so like we're actually not, we don't currently let you deploy a dependency even if it's binary compatible, unless you actually built with that dependency, right? So like if you upgrade the version of zlib in this DAG, it's going to change the hashes of everything, and you're going to need new build caches for that, just because we sort of force you to rebuild every time that happens. Right. That said, the next thing after this reuse is we're going to try to add a more sort of ABI-aware solver where we could do something like that. So if one of your dependencies updates, then you could, potentially substitute it into an old build of MVAPICH 2 that you didn't build that dependency with. Is that what you want to do, or is it the first case?
Yeah, I mean, that would be really useful, but definitely the first case where it updates all of the hashes is what we've struggled with, because we've seen that, like, there's an instance where NVIDIA added like dev versions.
Right.
So
right.
all of their specs changed to either dev or not dev, and ours were built. I don't think the actual package changed, but because we were built before dev not dev was an option, all of the hashes changed, which meant all of our GDR binaries became invalid, and we had to rebuild them all.
Yeah, I mean, it's not that they're invalid, right? It's just that Spack won't pick them up.
Right.
It's and which is just as annoying. So yeah, this will solve that problem, because if you throw some new binaries in the cache, I mean, it'll prefer the newer ones, right? Or it'll prefer what you told it to, but it won't forget about the old ones, right? And so if the user's Spack doesn't come up with the same hash as what's in the build cache, it sort of doesn't matter anymore, because we'll look at what's in the build cache and try to factor it into the solve. That's the big improvement.
Okay, cool.
Thanks, Todd. There is a question on the Q&A box.
Oh, cool.
Can you take a look, or I can read it?
So I think, I guess, okay. So the first one is hooray for autopackages.yaml. I agree. So I think, yeah, thumbs up. I guess I answered that. For second question from Adam Moody is, are we using Spack to install MVAPICH 2 binaries at Livermore? I think we are. I think Nate Hanford has done some of that, but I think it's been painful for him too. So I'm hoping that this will make it much easier for us to do that.
Yes, most definitely.
Yeah. And Kenneth says, oh, Kenneth is on this call too. Awesome. there has been a lot of discussion about supply chain attacks recently. See the SolarWinds mess. Do you take any special measures in Spack build caches to prevent attacks to inject malicious things into a build cache that end up being installed on the biggest supercomputers in the world? So right now, what we do, and I guess, so actually this is probably the relevant slide for that. We're talking about CI, right? The interesting thing about this CI is that the binaries that, if we made binaries available from this, the ones on develop would only be built from approved code. And what I mean by that is that there's actually a lot of stuff going on behind the scenes here. When we do builds on PRs with potentially untrusted code, the PRs actually get their own build caches, and they can reuse from those. If some PR is merged, we graduate the binaries from that PR to sort of a shared PR build cache so that all the PRs can leverage what's already merged to develop. But develop actually ends up rebuilding everything. And it's only the binaries that are on develop that get signed and that we would make available publicly. So, I mean, that's our sort of first line of defense, is that we would not put binaries out there that a human hadn't approved the recipe for. Beyond that, I mean, we do check all the checksums of the archives that we have. What we're not doing yet that we would like to do is to scan all the archives. And so I think actually with public services like VirusTotal and some of those other things, what we could do is every time we see a new tarball come into Spack, we could scan it. And that would at least give us some assurance that nothing nasty is going into the public binaries. So there's that. But like, you know, for source builds in Spack, we check all the checksums. For this CI workflow, yeah, I mean, we've taken a lot of care to make sure that the signing key doesn't get exfiltrated into PRs, and that only approved code actually gets signed and made public. And then, you know, if you're getting things from the MVAPICH team, you're going to have to trust them because they're providing the binaries, right? So that's going to be the big difference there. Does that answer your question, Kenneth? Or I guess maybe he can't talk.
He can, I mean, if he wants, he can talk. We can unmute him.
It's a really good question.
Okay. Are there any other questions for Todd? Okay, if not, thank again, Todd, for the things we started making your life a little bit harder, but I think you people have now a better solution.
No, you're making everybody else's life easier, so this is great.
Thank you, Todd.
Yep.
Thank you. Okay, so we'll then move to the next talk of the conference. It will be presented by Honggang Lee from Red Hat. Let me share his introduction. Yeah. So Honggang Lee is a software engineer in Red Hat. He's the maintainer of user space packages of RDMA stack for Fedora and Red Hat Enterprise Linux. And we have been working with him for some time to see that the integration of MVAPICH 2 takes place correctly with Red Hat stack. And he has been giving us a lot of feedback, and we have been improving on those. So I think Honggang will be sharing some of those insights, how we are interacting with him. Honggang, please proceed. I think your slides were coming, but it went away. Honggang, you are there? We might be having a slight technical problem. Samir and all, you can hear me?
Yes, Dr. Prano.
Okay. So let's wait for Honggang to, his screen was coming. After that happened.
So Honggang says that he can hear us.
But we can't hear Huh? We can't hear or see his screen.
Yeah.
We still cannot hear you.
No, Hangyang, we cannot hear you. We saw your screen sharing for some time, but then it went away. I think something happened with that. Can you reshare your screen? And you are unmuted, but we cannot hear you. Okay, we'll wait.
Now we can hear you. We were able to hear you for some time. Hongyan, can you speak? We can actually hear you for a little while.
Yeah, Hangyang, let us know. We heard a little bit of background noise from you, but after that, not. Alan, just checking with you in case there are the problem continues. Can we reorder? I'm just checking with you.
Sure, I can go whenever you want me to.
Okay. So Hongyang, if you don't mind, can we reorder? We'll proceed with Alan and we'll try to resolve your issues in the background. Then you can present after him.
Why don't we go ahead, Dr. Panda? Maybe he's trying to switch machines right now.
Okay. So send him a note. We'll switch. Sorry for the problem. I think let me introduce Dr. Alan Schussman, and then we'll get started. And